Okay, thank goodness I was only 8 minutes in the first time when I realized I didn't have my mic turned on, so I think I'm good to go now. So section 2 of chapter 9 is on analyzing rational functions. So what I was telling you before, when I didn't record, was that in your textbook there's a bunch of examples that are going to show you how we get to calculating this point of discontinuity and analyzing the rational functions. I'm not going to take a lot of time to do that. You can look in your textbook to see the theory behind it. I'm just going to show you how we actually do it. How do we calculate that point of discontinuity? So a couple of things that you need to know. The denominator of a rational function will give us a non-permissible value. And that non-permissible value is going to give us one or two of these things. One of them is a vertical asymptote. So once you have factored, if you need to factor, and the factors don't cancel and you're left with something, that means you're in your denominator, that means you're going to have a vertical asymptote at what's left. You will have a point of discontinuity if your factors cancel. So if you factor everything out and you're able to cancel something, or you're able to cancel everything out of your denominator, you're going to have point or points of discontinuity. So a point of discontinuity is just that. It's discontinuous. It means that at a certain point, your graph won't exist, and then once you go past that point, your graph will start up again. So to do that, what we do is we draw an open circle. So it's the point where your graph is not continuous, and we find it when, or it exists when, you have a denominator that has a factor that will cancel. So we're going to try some of this. So we want to sketch the graph of x squared plus 2x minus 3 all over x minus 1. So in order to do that, the first thing we have to do is factor where we can. So fx is equal to, this is just a product and sum, product of negative 3, sum of positive 2. So that's going to be x plus 3 times x minus 1 all over x minus 1. Now you have to remember when you're canceling, if you can't cancel a whole factor, then you can't cancel parts. So I couldn't cancel my x with my x and my x plus 3 because I'm not canceling the whole thing. But I can cancel x minus 1 with x minus 1. So this leaves me with x plus 3. So according to my definitions, rules, whatever you want to call them here, if a factor cancels, then I have a point of discontinuity. So I'm going to have a point of discontinuity at x is equal to 1. Well, what is my y value then? If my x is equal to 1, what I do then is I substitute into here. Y is equal to x plus 3 is what I'm left with. So y is equal to 1 plus 3. Whoops, 1 plus 3, so y is equal to 4. So my point of discontinuity, the actual point, will be at 1, 4. So the vertical asymptote occurs if there's a factor in the denominator that does not cancel. Well, in this case, in this example, everything canceled out of my denominator. So that means I'm not going to have that vertical, that dashed line going through. It just doesn't exist. That means that all of my y values will exist except at this one particular point. So if I look at this, what I'm left with, I started out with a quadratic. Okay, I had an x squared, and now I've reduced it down to a degree of 1. Well, a degree of 1 means it's a linear function, so it means I have a line with my m value, or my slope value, at 1, and my y-intercept value, or the b value, at 3. So if I go to draw this, this is my y, this is my x. So I know at the point 1, 4, I'm going to have a point of discontinuity. So 1, 4, right here, I'm going to have an open circle. At 3, I'm going to have a y-intercept, so that's, remember, that's the point 0, 3. And then from there, my slope is 1 over 1, so I'd be going up 1 over 1. That's my point of discontinuity at 4, 1, so the next one would be at 5, 2, and then I would be at 6, 3, and so on. Going down, I would be, excuse me, at 2 and negative 1, and then it would just keep going. So my graph, when I draw this, is going to go like this, go up to that open dot, and then continue. Pretend that's a straight line. That graph is done. I've drawn it. I've included my point of discontinuity. I don't have any vertical asymptote, so it's finished. Okay, so let's look at the next example. It says compare the functions of x squared minus 3x over 2x plus 6 and x squared plus 3x over 2x squared plus 6. So first thing I have to do is factor. So from the top here, I have x times x minus 3. On the bottom, I have 2 over x plus 3. Okay, so I can't cancel anything, and according to my 2 rules at the top, if a factor does not cancel in my denominator, that means I have an asymptote. So that means I have a vertical asymptote at x is equal to negative 3. Point of discontinuity is if something canceled. So this one, there is no point of discontinuity. And that's because nothing canceled in my denominator. Sorry, this is so messy. Okay, so let's look at the gx function. So I can GCF an x out of there. I'm left with x plus 3. In the denominator, if I GCF a 2, I'm left with x plus 3. So my x plus 3 and my x plus 3 will cancel. I'm left with x over 2. So that means then I have a point of discontinuity at x is equal to negative 3. So that means if I substitute, I would have, this is what I was left with, y is equal to x over 2. If I substitute in my negative, or my x value, negative 3 over 2, so my point of discontinuity would be at negative 3 and negative 3 over 2, or negative 1/2. This one, because I'm not left with anything, I'm not left with a variable in the denominator. I have a constant, but that's not, because I can't go 2 not equal to 0. It doesn't work. So that means that I don't have a asymptote, because I don't have a non-permissible value. Okay, next one. It says, match each rational function with the most appropriate graph and explain your reasoning. Okay, so let's take a look at our graphs here. Actually, let's take a look at the equations. So I have kx is equal to x squared plus 2. So if I go to factor this, x squared plus 2 doesn't factor. On the bottom, I have x squared minus x minus 2. That's a product and sum of x minus 2 and x plus 1. So if I have factors that don't cancel in the denominator, I have vertical asymptotes. So that means for this graph, I have asymptotes at x is equal to 2 and x is equal to negative 1. So all I did is I took my 2 factors in the denominator, put them equal to 0. So x minus 2 equals 0, x equals 2, and then x plus 1 is equal to 0. So x is equal to negative 1. Because nothing canceled out, I don't have a point of discontinuity. So that means I'm going to have graphs where I'll have two asymptotes and no open dots on there. So you can tell by looking at this right off the bat, and I'm going to finish doing them all, but this third graph has two vertical asymptotes. It's the only one that does. So I'm pretty sure that that's the graph I'm going to go with. It also has no points of discontinuity. But let's try solving the other ones. So Lx is equal to x minus 1, can't factor, but I have x squared minus 1 on the bottom, so that means I'm left with x minus 1 times x plus 1. That's just a difference of square. So if I do my canceling, this and this cancel, so I'm left with 1 over x plus 1. So the factors that don't cancel leave me with an asymptote, so that means I have an asymptote at x plus 1 equals 0, so at x is equal to negative 1. My point of discontinuity then happens where the factor canceled. So at x minus 1 was my factor that canceled. So then that means x is equal to 1 is where my point of discontinuity is. To find out what my y value is, I substitute into what I'm left with, that 1 over x plus 1. So this is 1 over 1 plus 1, so that's a half. So my point of discontinuity then is going to be at negative 1 and 1/2. So my third equation, m of x is equal to x squared minus 5x plus 6. So that's another product and sum, product of 6, sum of negative 5. That leaves me with x minus 3 times x minus 2. On the bottom I have 3 minus x. So 3 minus x and x minus 3 are exactly the opposite. So I could just rewrite this as x minus 3 times x minus 2 over negative x minus 3. So if I factor out a negative from my denominator, this 3 becomes, positive 3 becomes negative 3, negative x becomes positive x. So now I can cancel. I'm left with x minus 2 over negative 1, if you want to leave it there without doing any further simplifying. Okay, so my two rules are, first one says if something cancels or does not cancel, then I have a vertical asymptote. So if I look in my denominator, everything canceled. So that means no vertical asymptote or no asymptote. If something cancels, then I have a point of discontinuity. So my point of discontinuity for this one is at x minus 3, so it's at x is equal to 3. So I do my calculation, I was left with y is equal to x minus 3, so 3 minus 2 over, over negative 1. So that is 1 divided by negative 1, so that's just negative 1. So my point of discontinuity occurs at 3 and negative 1. So now I take a look at these and see, okay, what goes with what. So my first one there, my kx graph said, there's no points of discontinuity, but I have two asymptotes at x equals 2 and x equals negative 1. None of my other graphs had 2, so I know that this goes, x graph 3 goes with that graph. The next one, x minus 1 over x squared minus 1. I have one vertical asymptote at x is equal to negative 1, and I have a point of discontinuity at negative 1.5. So I have one asymptote. Point of discontinuity right here is at 1, negative 1/2. So this is graph 1. So then that means that by default, My third equation is graph 2, but if I check this, I should not have a vertical asymptote, and I should have a point of discontinuity at 3 and -1, and I do. So that's all there is to matching these. It's finding out what is your vertical asymptote, or if there is one, and finding your point of discontinuity if there is one. I'm just going to do a couple of other equations just for you to have some practice of finding that vertical asymptote and point of discontinuity. Yeah, there's quite a bit of room here, so I'll do one on here. So this is going to be my equation. F of x is equal to x squared plus 3x over x squared minus 9. So my first thing is to factor. X squared plus 3x becomes x times x plus 3. X squared minus 9, difference is square, so that's x plus 3 times x minus 3. Cancel. I'm left with x over x minus 3. So remember, if a factor does not cancel, that leaves me with a vertical asymptote. So I have an asymptote at x minus 3 equals 0, so x equals 3. I could calculate a x-intercept, or sorry, a y-intercept for this. Well, you could do x-intercept too if you wanted to. And you could calculate a y-intercept if you wanted to as well. Not necessary though, but you sure could. When it comes to if you have a graph where your asymptotes ended up being the same, and you might have maybe your point of discontinuity was the same, then maybe you might want to take a look then at your x and y intercepts to see if there was something different in there. Or if maybe they both had asymptotes at x is equal to 3, neither graph had a point of discontinuity, then you calculate your x and y intercepts. So okay, now I look at my point of discontinuity. It's at the factor that canceled. So I have x plus 3, so my point of discontinuity is at x is equal to x plus 3 equals 0, so that's x is equal to -3. So that means when I substitute into my equation here to find my y value, I have -3 over -3 minus 3, so that's -3 over -6, so that's 1/2. So my point of discontinuity will be at -3, 1/2. Okay. I'll just do one more. So if I have g of x is equal to 3x over x squared minus 9. So kind of like this one, but a little bit different. So 3x and x minus 3 times x plus 3. So this one has two factors that I can't cancel. So if I can't cancel them, that means they are going to be vertical asymptotes. So this one means I have vertical asymptotes at x is equal to 3 and x is equal to -3. I don't have any points of discontinuity because nothing canceled out. So this is a case if it asks me to match it with a graph where I might need to go then and find my x-intercept and see if that helps me get a little bit closer. So if I did need to find my x-intercept, I let my y equal 0. So I have 0 is equal to 3x over x squared minus 9. So if I cross multiply, 0 times x squared minus 9 is 0. 0 is equal to 3x. So that means that 0 is equal to x. So my x-intercept would be at 0, 0. Okay, so the last little key ideas here is that the graphs of rational functions have a vertical asymptote or point of discontinuity that corresponds with the non-permissible values. Okay? So if something cancels, then that means you're going to have a vertical asymptote. If it, sorry, I said that wrong. No, I said it right. If a factor doesn't cancel, you're going to have a vertical asymptote. If it does cancel, you're having a point of discontinuity. You can find the x and y intercepts and the vertical asymptotes by looking at the numerators and the denominators. And then it says to analyze the behavior of a function near a non-permissible value, use the table of values or the graph, even though the function is undefined or does not exist at that non-permissible value itself. Okay? So you can tell by looking at it where that point of discontinuity is.